Next we will learn out direction of a vector. How can we represent or give a direction or judge the direction of a vector that is in the same direction as the given direction or a direction opposite to the direction of a given vector? As we know that a vector is associated with a particular direction. That is a property of a vector because vector is a quantity that describes magnitude as well as direction. So vector is also associated with a particular direction. So if vector x and vector y be two vectors in R square two-dimensional geometry or R cube three-dimensional geometry, and if vector x is equal to ky and first case what can be happen if k is greater than 0, then vector x and vector y have same direction. And if k is less than 0, then vector x and vector y have opposite direction. And what happens if x and y have neither same or opposite direction, that is vector x is not equal to k times vector y, then these vectors have different directions. That is, they are located independently. They are located in a plane. Maybe both in line same plane or in different plane. If some vectors have opposite or same direction, they must lie in same plane. For example, 1, minus 1, 1 and 2, minus 2 and 2 are two vectors. Then we can see 2 minus 2, 2 can be written as 2 times 1, minus 1, 1. That is k is equal to 2, that is greater than 0. Therefore, vector x and vector y have same direction. And if k is less than 0, then they have opposite direction. Now what happened? Just judge vector minus 1, 1 and minus 1 and vector that is 2 minus 2 and minus 2. So we can't represent this vector in the form of this vector. So these two vectors, that is 2 minus 2 minus 2, if we take 2 common, it becomes 1 minus 1 minus 1. Or if we take minus 2 common, then it becomes that is minus 1, 1, 1, which is not equal to k times minus 1, 1, minus 1. That is vectors minus 1, 1, minus 1 and vector 2, minus 2, minus 2 have different direction. Therefore, by using this criteria, we can find out whether the vectors are in the same direction, in opposite direction, and or they place in the different direction independently. That is, they are not dependent on each other. Now we are going to state a theorem which is based on magnitude and direction of a vector. It gives the concept or relation between magnitude and direction of a vector. So theorem 1 is non-zero vectors, vector x and vector y are equal if and only if their magnitude is equal and vector x and vector y have the same direction. So, the proof is, first of all, suppose vector x is equal to vector y. That is vector x with component x1, x2, x3 and vector y with component y1, y2, y3. So by quality law of vectors we get vector x1 is equal to vector y1, x2 component is equal to y2 component, x3 component is equal to y3 component. Now we will check its magnitude. Its magnitude will be given by vector x, that is under root x1 square plus under x2 square plus x3 square. As x1 is equal to y1, so we replace x1 by y1. It becomes under root y1 square plus y2 square plus y3 square, as x2 is equal to y2 and x3 is equal to y2. So it becomes the magnitude of vector y. So if vector x is equal to vector y, then magnitude of vector x is equal to magnitude of vector y, and also we have as vector x is equal to vector y. If we compare it with vector x is equal to vector k times vector y, then it gives k is equal to 1, which is greater than 0. That is, vector x and vector y have same direction. Thus, if vector x is equal to vector y, that implies magnitude of both vector is same and vector x and vector y have same direction. As it was related to if and only if, so we'll discuss the converse part. So converse is suppose vector x is not equal to 0 and vector y is not equal to 0. That is, one of its component must be not equal to 0. And we have magnitude of vector x is equal to magnitude of vector y, and vector x and vector y have same direction. Now we have to prove vector x is equal to vector y. Since Vector x and y have same direction, therefore, by definition, vector y is equal to k times vector x, or we can say vector x is equal to k times y for k greater than 0. Now we will find the magnitude of vector y, that is equal to k times magnitude of vector x, which becomes modulus k times, that is modulus vector x, that is magnitude vector x. But we have magnitude of vector y is equal to magnitude of vector x. Therefore, number 1 becomes magnitude of vector x is equal to modulus k, that is magnitude k, and into magnitude x. On cancellation of magnitude x, as is a positive quantity, we get magnitude of k or modulus of k is 1. As k is greater than 0, so we'll take only value of k as positive. Negative value is rejected. Therefore, vector y is equal to k times vector x gives vector y is equal to vector x. That is, as vector y and x have same direction, vector x is equal to vector y. So, theorem is proved, that is, if vector x is equal to vector y implies, that is if and only if, magnitude of vector x and magnitude of vector y is equal and vector x and vector y have the same direction. So we see the converse is also true, that is, if magnitude of two vectors are same and two vectors have same direction, that will happen only if and only if both vectors are equal. So this is a theorem which was based on magnitude and direction of a vector. Now we are going to state theorem 2, which is based on concept of unit vector. So theorem 2 states that if x is a non-zero vector, then there is a unique unit vector in the direction of vector x. So we have to prove, if a non-zero vector exists, then there is a unique vector, that is unit vector, which is in the direction of vector. So the proof is, as x is a non-zero vector, so its magnitude is also is non-zero. Therefore, we define, let y is equal to vector y is equal to vector x over its magnitude, which can be written as k times vector x, where k is 1 over modulus, that is magnitude x, that is always a positive quantity, that is greater than 0. As k is greater than 0, y becomes k times x. So we will find the magnitude of y, that is magnitude of vector x over magnitude of vector x whole magnitude. It becomes magnitude x over double magnitude of vector x. So that is vector x magnitude, and magnitude of vector x is again magnitude x. So it gives 1. As magnitude of vector y is 1, therefore by definition of unit vector, vector y is a unit vector And as we prove vector y is equal to k times vector x with k greater than 0, then vector y and x in same direction. So we can say then vector y is a unit vector as it is proved unit vector in the direction of x. So one part is proved there is a vector unit vector in the direction of a non-zero vector. Now we have to prove uniqueness of vector. So let Z be a unit vector in the same direction as vector x. Then as Z is a unit vector, so its magnitude is 1. And also we have magnitude of vector y is also 1. That is magnitude of vector y is equal to magnitude of vector z is equal and x and y in same direction. Also x and z in same direction. That implies y and z in same direction. So as we proved in theorem 2, if two vectors have same magnitude and are in the same direction, then these two vectors are equal. Therefore, by theorem 2, vector y is equal to vector z. That is, z is same as y. Z is not a different vector. Therefore, uniqueness is proved. Hence, we can say there is a unique vector in the direction of a non-zero vector x. Hence, the theorem is proved.